lattice Boltzmann on.
Oh yeah? How's that going?
So far so good, I guess. I was originally going to be coding the lattice entirely incorrectly for like lattice Boltzmann.
Oh good.
So I went up to Wagner and like, okay, is this like how it's supposed to be done? No. Like,
So you're doing you're using lattice Boltzmann with molecular dynamics.
yeah.
Adjacent.
Yeah, so it's like the end game is like a 3D.
Here's the place where you can relax.
And then a sheet of molecular dynamics, and then having those things like
That was a
interact
full 3-hour
appropriately.
lab today.
And the sheet can conform and bend and all that.
So how do you model the interaction between the molecular dynamics and the lattice Boltzmann?
That's the tricky part.
That doesn't make sense to me.
You have to like have some kind of mass. You have to figure out like which links are getting broken. So like, say you got like 2 lattice points or whatever in like the 1D lattice case, I guess, which is what I'm trying to do right now. Is just kind of like work my way up through the dimensions.
Well, I'll start somewhere.
Yeah. So like you got your 2 lattice points here, right? And you got this point in between because it should be like 1 less dimension than the lattice. So like say I have a like a density or whatever that's wanting to go that way.
Yeah.
Well, then it should bounce off the wall, go back, and impart some momentum on the sheet.
Oh,
So then the sheet would move a little bit, or accordingly.
okay.
And then you'd have
No,
like, your vector going back the
I've
other
been
way.
asking around.
And then I guess also like I'm thinking if
A couple others there can't make it.
I haven't really talked to Roger about this part yet.
So we will go through very similar material for 3 times, and if someone is missing today, in part it will be repeated next times. What we do is a little more complicated compared to what we did before, but it's definitely easier than lattice Boltzmann. Because we will stick with 1 dimension instead of whatever you have there. So, what you can do today, except winning back and relaxing. So, did you get the email with the code? Just very simple. Run it, play with it, make a copy, and then start playing with it as kids play with toys, like tear off the head. Try to make it to stop working and look what is inside. If you are so meticulous and you want to convert it into true academic studies, you can look on the printed version of the code and make marks like what each line is doing or what your favorite line is doing. Or you can type comments there. So let's maybe run it and see what happens. So after you have this image popping up, you can click enter and see what happens. And Braden will become very happy. So what do you see? So can you what do you see first, maybe second after you keep the enter? Before this panels pop up.
Is that the thermal
Why me
peaks?
specifically?
Is that
Because
the
of the
talking
animations.
today about thermal peaks?
Really?
No. Just tell by your own words what do you see?
Multiple peaks separated from this one loop, right?
Yes. I don't know if you need to record this discussion, but. Oh. So what did you tell me?
When you played the animation, it's multiple peaks split from this main one right here, moving towards the right of the graph.
Okay. Yes. Maybe if you just run the code that I said. So you are absolutely correct. I did a poor homework and didn't label the axis, so I wouldn't give good grade to myself. But let's guess what is on the axis. what are the options? What is x-axis? What is y-axis? What are your suggested guess?
Probability and time.
Yeah.
Oh.
So we were really happy today in class because we touched real life with many levels. I wish we approached the same level of connection to real life again, but now we are returning kind of a little backwards to simple models, but on the much higher level. So position. X is position, Y is probability. Make sense? Run the code once again. So I sent by email, just download it. So you'll see that the peak here should launch and go forward a little bit. Right? So if you remember presentation by Braden 2 weeks ago, he was illustrating the width of the wave packet increasing in his animation. Here is the so here you are observing the same effect combined with translation. So guess which model are we returning back to? Huh? Well, it is method. Method is like solving time-dependent problem. But which model? Like, is it
Particle in a box.
Where are the walls of the box? Maybe there are walls and we just explored the model for too short time, so it doesn't reach any walls.
Yeah.
Right?
That's a free particle.
Yes. So I know that you may become again a little upset. So we return from these nanostructures back to free particle, but we need to sharpen our teeth to return to real models with more skills. So this is free space. So the Hamiltonian has only kinetic energy, no potential, one-dimensional. And we are looking for this Gaussian-shaped particle, and we see how it moves in time. When we worked in class by analytical methods, we did what? We suffered. we did apply different methods for different key features of this particle, of this wave packet. So we were separately treating the separate treatment for average position, how it moves, this Heisenberg equation of motion, and we were going forwards and backwards between momentum representation and position representation for the width, right? I hope we will not do it again. And I will try to make us to avoid it, to avoid it in pen and paper calculations. So this code does it all at once. So all aspects of free particle motion. And the little changes of this code will deal with any one-dimensional problem. So basically it is main instrument for the rest of the course. Well, we will make a little bypasses to different things, but this is something that we may look at again and again and applying the same code for different systems. So for next 3 labs, we will just slowly chew it and make ourselves proficient in it. With like 1 line change, you can adjust this code to any system you want. Like nanostructures, molecules, electron transfer problems, like Markov theory for Nobel Prize 60 years ago. Transition state analysis, something related to real chemistry. But now we are just exploring the methods on the example of free particle. Make sense? I know it is maybe not super exciting, but how do we plan our activity? What do we do? Focus on this word. So we can go through the line by line and see how it operates. Why we should do it? Because later we may want to skillfully use it to try realistic problems. And we can look on the code from different aspects. 4 pages is not too much, but it is a little boring. 4 is 3.5. We can just go line by line, or we can approach strategically, like guess which parts should be there, and then try to identify it there. What I suggest, we will make your free will votes to make presentations based on this code, so that all aspects related to it will be covered in same style as we did postulates and MATLAB skills. And then after we get through, we will try to apply it to more and more systems, and maybe at the end of the course you will select a system of your dream from your realistic research, trying to do one-dimensional lattice Boltzmann maybe, or whatever your research favors are, and see how this approach, which is in some sense exact numeric approach, can help you to solve your favorite scientific problem. So relax, I'll tell you when to concentrate. Which ways of predicting future do you know? Based on what we had in the course. So the most standard is Eigenvalue Expansion. It is what we practiced last time here, and what you see in all textbooks, and what you will see in the homework. I cannot make any homework related to the labs. Right now we are investing in the mid-future, not next due period, but a little later. So whatever you do for the homework right now is eigenstates expansion. This one is in between first and second method. This code, when we will go through the code, you will see that it does have the evolution operator, but instead of evolving everything at once from past to the specific period in the future, it will make infinitesimal increments, more to the future. And in this sense, it is closer to the second method. So, same way as you did in the completed homework, with question like, what do you need as an input and what you get as an output when you predict future? As an input, you need initial wave function and Hamiltonian. As an output, you have wave function at a specific time larger than t, and that's it. Right? So this is what we start from. Then we use one of the things that help to find the future. And then we use our knowledge of the future by predicting some observables that are potentially useful to describe experiments or satisfy our scientific curiosity. Make sense? So, observables at different times. And then there are, I wouldn't say trivial, but standard things of accumulating observables at each point of time, plotting them or saving them, same as you already shown your proficiency in the MATLAB presentations. So when we are looking through the code, we may want to identify these steps, like initial wave function, Hamiltonian, evolution operator, propagating in time. So I'm not requiring anything, and I even do not know how to set up a question that can be for grading or whatever, but you may try to mark places in the code that seem relevant to this concepts. And sometimes in the class I will put a release a sign-up sheet where you will select which subject you want to study in more details and present. Okay, so what should we start from? Right now it looks, if I imagine that I see it for the first time, it looks scary and not very organized. But we will get through. So if it would be very boring to go line by line. If we are looking for time propagation by infinitesimal steps, then we should have a loop over time, right? And we do see that I have erased some lines that are senseless, so it is a little different indices in what I've sent you, but the printout has the same label. So number 73 is begin of the loop. And if you look on the first line of the declaration of loop and the fourth line after declaration of the loop, you will see psi number 2 equals something that is called E tau times psi 2, right? Do you see this point in the code? So what does it mean? See? No, it is G tau. So let's try to correlate it with what we had in the course before. How can we, well, if we are repeating it in the loop, I'm guessing that here is wave function of the near past. Here will be wave function at the near future. Tau will be our increment of time. Delta t equals tau. And then, which object helps us to go from the past to the future by multiplication?
Operators?
Yeah, well, if you multiply something on the wave function, it is definitely an operator. But which operator?
Time evolution?
Huh?
Time evolution?
Yes, time evolution. So propagation, time evolution operator. GT is time evolution operator. Time evolution operator. So So we already have something about time evolution period. Well, when you run the code, how many? When you just run the code, not at the end, there is a popping up several panels. Maybe they're interesting, but for the first glance, it's like garbage, too much. But when you're just starting, how many lines do you see? 1, 2, 3.
1.
And when you propagate in time? Yes. How similar or how different are they? But let me run the code once again and repeat this question with the specifics. Or maybe just pop up this one. So you start with one line, and then as time passes by, they develop into two. But both of them move from the left to the right. Both of them expand. So show some broadening. Cover everything. But they're a little bit different. How would you interpret it? Like, no knowledge of physical chemistry or quantum theory from the course is needed, just from the common sense. What could it be? For example, you are taking spectrum, and you have the recently purchased shiny equipment, and you have an obsolete equipment of 30 years old. They give qualitatively the same trend, but they have different resolution and maybe slightly off in the absolute values. Right? Or, so it is if you are from experimental point of view. If you are from the theory point of view, well, theory is too boring and rare, but computation, which is like simple theory. When instead of concentrating your brains, you concentrate the brains of computers. You can compute the same observable by different methods and get slightly different results, right? Or you can, if you're doing theory, you can slightly toss different level of approximation and also get different results. So you see how the precision of your answer depends on approximations that you employ or do not employ. So basically it is the same thing, but computed with different approximations. So what we will have, there will be 2 or 3 methods hidden in this code. There will be same thing computed 3 times, so that we can compare and what we judge, what we trust better. I know if you start right away, it is a little too much weight, but later it adds you strengths when you try to sell it in your future life. Like, here is one method, here is another one, this one is more trustable, therefore accept my paper. Here's the logic. Or whatever, give me all degrees right away. So, time evolution operator. How were we writing it in class? G propagates from time t to time t plus delta t, which to tau. Yes. What should I write?
No.
I shouldn't write. What should I write? How do you formulate time evolution operator? Roughly, what should be there?
Exponential of the phase accumulation.
Perfect. Can it be better? So we put exponential h bar times 2, right? Well, if we would like to be precise, we would put integration Hamiltonian time dependent, but since our tau is small, so it's delta t, in fact, tau is just a symbol here, this will be sufficient. So let's put a microscopic goal, browse through the code and identify where this g tau is defined. And we will be seeking for time increment, for imaginary unit, for Planck constant, for exponential, and for Hamiltonian. And I can mark it for myself. What is it? Infinitesimal propagation by time evolution operator.
Oh.
So I'm scrolling up and looking for g tau 2. I already see g tau 3, so it should, third method, and nearby should be g tau 2. Okay, so it is what we were looking for. I guess this is time evolution. So, who helped me? Brilliant. About exponential and phase accumulation, right? So it should be increment, exponential. It should be time increment. It should be Planck constant, should be imaginary, should be EXPM. And now there is a CHEM. CHEM is, in common language, is food. But here we deal with quantum theory and physical chemistry. So what does CHEM2 stands for?
Hamiltonian.
Yes! So Hamiltonian by second method. And if you look one line above, we will recognize something that we can correlate with the course material. So you see here P sub x squared divided by 2 mass plus V. So P squared over 2 mass is likely kinetic energy and V is likely potential energy. So the code is more or less general, but if we scroll up, we probably should identify that V is set to 0 to describe free particle. But later on we can modify the V. So what do I do? Kinetic plus potential energy operator. So how do we read the code further? What should we focus at? With our general strategic understanding what it does. It is the same. Whatever was sent by email and what is printed is the same. I just erased a couple of lines to make it shorter and fit into 4 pages.
Oh, okay.
So some unnecessary print.
Didn't know there were 2 sided. I was very confused. I was looking at 1 of 4 and 3 of 4.
I know this task is at least 4 times more heavier than anything we did before, because before all our codes were 1 page long. So we can keep unwrapping what is Hamiltonian, which should be px squared over 2m. So x just stands that we have x dimension. If you want, you can rewrite this code with py and pz for 3-dimensional motion plus v. So we may identify these components. What else can we learn from the thing that we observed inside the loop? We can identify the variable, or not variable, the array, the function that will represent the wave function, the function that will represent the wave function as we go through the time. So probably it will be a function that will be modified at each time step, and that we will be updating every time. So we have past, then we update it, and then we get future. And we may realize which function stands for it. Which one? I think it was psi2, right? Okay, so it will be wave function as specified at each time step. But if you want to propagate it in time, we need to start somewhere. We need to know our past. So we need to know initial conditions. So let's just browse through and find where it comes at first place. Where do we start before the loop? So let's focus on initial wave function. Before we do, let's main principle, least action principle. Do less, think more, if possible. You did a lot of breakthrough steps in physical chemistry and quantum theory, and you have general idea how the centralized wave function should look like. We did a couple of homeworks, and you know your favorite, well, I don't know if favorite, but a function that we dealt with for several classes. So the bell-shaped function has name of
Gauss?
Yes, Gaussian function. So, and when we did run the code, we saw that at the initial time it was like sharp bell, right? So when we browse through the code, we should see something that has exponential of x squared. Maybe with some specified initial position, maybe by some way the momentum is defined, but we will look for initial condition arranged in shape of Gaussian function. Let's go through and let's look for psi2, like where it is. Okay, see what I discovered. In line 49 we see psi2 equals psi. So, and it happens before we launch the loop. The loop is launched in 73, and this let me record right away what is here. The wave function before the loop started has been set to be equal to initial condition. Let's look for object named psi. So if you scroll up, we should see something named psi. So I'm going to scroll up. Scroll up. Huh. Okay. it tells that psi is set to psi naught. So the notation psi naught. Finally, we found it. Initial wave function is psi naught. Where is it defined? I'm so curious.
So question, why is it so convoluted in a way?
Huh?
Why is it so convoluted? Like, why do we have to start with psi 2 to go psi equals psi naught?
Because we want to have several methods that compute the same thing,
Okay.
and we want them to start from the same initial condition. So psi will be for method 1, psi 2 for method 2, and psi 3 for method 3.
Oh, okay.
And psi, the psi without number, which is psi 1, by
Yep.
this corrupt logic, is not as promising. We will look on it later. The method 2 is most natural. The first and last are less natural, and it is a waste of time to look on them first place. So this, we say, convoluted, non-linear logic is made to, it is against the principle of ancient Romans. Instead of divide and conquer, it's principle of a greedy person, put everything together.
Yeah.
It doesn't look nice. Maybe some of you will clean it up and then pass it to next generations. But I don't know. So, curios. Should be the letter U here? Curios or curios? Curios. I'm curios. I am so curious. Psi naught. Aha! Initial Gaussian at time 0. Even if I do not recognize, and let me break the line here just that we can see it all. So I'm looking on line 22, and it should be initial condition. So psi naught of x in time 0. So you recognize it should be minus x naught squared divided by some width parameter. It's the only thing that I remember from the class. Maybe you remember more. So there should be some normalization factor. But if you look here, we may see some surprises. Let's compare our expectation for this equation and what is written here. Well, exponential, open bracket, close the bracket. That's fine. X minus x naught squared divided by this 4x var. So probably 4x var is what we have here. 4x var will be variance, width parameter. So if we scroll up again, we can find that this parameter of width will tell whether we have sharp or extended initial width of the waveband. But we see some other terms. So, well, this x var comes to the normalization. So we have 1 divided by 2 pi x var square root of square root, or square root of power 4. If some of us was carefully doing homework or looking through materials, we can recognize that there was a normalization factor with square root of 4th power. Okay, it's not a big surprise. It's a technical detail. Then we have square root of dx, which put a little, like, why should I put square root of dx? But again, no big surprise. You can just understand what is going on later. But we do see an additional term that we haven't seen before. So the whole thing is multiplied by exponential of IP naught times x minus x naught. Close the bracket. Do you see it? Do you see it here? So how do we interpret it?
Projection of some kind?
Okay, not wrong, but other more comments or ideas. What does it look like? Where have you seen expressions like e to the power of imaginary unit momentum times position? Does it look to one of the few functions that we learned through our short life as physical chemists?
Plane wave.
Plane wave. Did you hear it? Does it click? So we multiply Gaussian wave function by a plane wave with non-zero momentum. So we just make a merger, hybrid, descendant of two parents of Gaussian wave function and plane wave. And then what do we see as a result? Our initial wave function, Gaussian wave function, doesn't stay in one place. It moves from left to the right as a result of this product. So if we define wave function as a product of Gaussian shape times plane wave, and we set up the specific value of initial momentum, it will make overall wave function to travel in space with a given momentum. So we expect that center of wave packet will move with this p naught. So this, to some sort, this wave function is initial condition. But if we restrict ourselves with Gaussian wave function, then our initial conditions are 3 parameters: position, momentum, and width. So initial momentum. Is it just an exercise to dry young brains and make the course adverse and unpleasant? Do you feel a smell of any benefit from specifying initial conditions in this way? Try to unleash your imagination. When do you want to give a kick to an electron? Or maybe not electron, maybe some other particle that has quantum properties. Please try to think for another minute. Okay. Who needs P naught?
Without it, nothing would happen with no potential.
Hmm?
Without it, nothing would happen without a potential.
Well, later we'll add potentials. Let's look forward to, let's say, 2 months or month and a half. Which benefits you may imagine of having initial momentum of an electron? Like electron gun with electron smashing into kinescope. But it's too much of physics. From point of view of chemistry. Well, maybe physics doesn't need kinescopes anymore. Ideas? No? Maybe you have ideas, but you do not feel comfortable disclosing them. Well, I know the answer, and I just do not want to show it right away. Maybe you have seeds of your own ideas, and let's see if you are thinking in a similar direction. So most of us are employed or whatever, working at doing research at chemistry department, looking at reactions. Chemistry is bond breaking and bond formation. So atoms coming closer to another atoms and staying there stable. And some reactions can be like one molecule smashing into another one, or in a simplest way, can be instead of molecule, it can be like radical or a proton. So proton smashing into molecule and protonating. Proton is a so small particle that it has quantum features. And molecule has its potential profile. So what if you consider protonation reaction, like accelerating a proton and making it bump into a molecule, experiencing which potential this molecule has. So we will just replace somewhere here should be mass. We will replace mass of electron to mass of proton. Set up this V as a V of a realistic molecule, and put the momentum of the proton to whatever we see it in a reaction. Like momentum that will generate room temperature, or momentum that will generate energy, average energy at the detonation of TNT, or whatever reactions we want. So setting up initial momentum opens us a door to describing chemical reactions in the future. Right now everything is boring, electron in a free space, but same tools, same principles will be applied to very, very chemical problems. And it's too early now, but I'm giving you seeds of thoughts. Please start thinking of which research project you would like to pursue as a part of this course. This question will be raised maybe in a month from now, but we will accumulate enough muscles, enough skills to attack almost any problem in chemistry, physical chemistry, and I can offer challenging and interesting and exciting problem for each of you, but maybe even what is exciting for me will be not exciting for you. So you better design something that you like. So who needs P-Note?
Chemists?
Yeah. It was where do we go further? So we do have initial condition. If you scroll up, probably we should find 3 parameters of initial condition. P naught, X naught, and X var. Let me make a little record what we did. Initial Gaussian at time 0. Who needs P naught according to Braden? Any chemist needs P naught. I'm not lying. You've told he told this, right? Well, is it good or bad? But no violation of author rights. Thank you for helping. What else? This equation includes 3 parameters of initial condition. Position X naught, momentum P naught, and width width of initial wave function X var. Let's scroll up and find them. Scrolling up, and we are on the line 22, so it is not too much space to scroll up. Haha, See, they are almost at the very beginning. P naught, X naught, X bar. This is my favorite parameter. Momentum that each chemist needs. Initial position and X var width of wave packet. Width of wave function. So where we are and what are we doing? What is the major difference from our chemistry that we do here in the lab and true physical chemistry that we do right now in the class? So in class, we are going, so to say, canonical way. We are expanding any initial condition over eigenfunctions. Here, we are forgetting this canonical way, and we are just setting wave function and propagating it forwards in time. Why? What is wrong with all generations of quantum theorists? Why don't we do the same code that functions for the same problems, but with eigenfunction expansion? Okay, please develop your ideas. You do not need to speak up, but why this code that we already looked through and we didn't found eigenvalue? We have Hamiltonian, but we do not have eigenvalues. We do not have eigenfunctions, but we still claim that the code will be universal. What's wrong, or what is good? So if we would go standard way, we will need a set of basis functions, which are preferably eigenfunctions of Hamiltonian. But we want to be so universal that the code will not depend on Hamiltonian. Hamiltonian will be, and potential will be plugged in and solved. And well, if we look for problems like particle in a box, where electron is confined, claustrophobic, then there is a finite number of what? Of levels, of eigenstates, of eigenfunctions. But if you, let's make a broad appeal to chemical audience. If we have explosions, if you have combustion, if you have dissociation reactions, come to me. So dissociative reactions, meaning that your potential may have some features, but then it goes down and without features, right? The further away, the more free electron is. Or it's maybe not electron, maybe proton dissociation, or some radical dissociation, or even just molecule breaks on two pieces and they fly away. And for potentials for dissociation, there are too many eigenstates, too many eigenfunctions. Basically, for free compounds, eigenfunctions are plane waves. And plane waves are dense like crazy. There are an infinite number of plane waves in any region of energy. So if you would formulate a problem like this on the language of eigenvalues, we should limit ourselves to confined electrons or confined molecules. We would prevent ourselves from describing dissociation reactions. Right now, no problem. We can do theoretical combustion or theoretical explosion, which looks like a very attractive thing to do and very safe compared to experiment. Make sense? Okay. What else should we look at? Well, since we are in atomic units, the Planck constant is 1, mass of electron is 1. Right? We should cover atomic units sometimes in the class, but you may be aware of them. If not, it's not a problem. It's brief. Let's make an experiment. What if we double the value of the momentum parameter? Let's look for it. P naught equals 2.5. What if you set it to like 5 or 10? What should we see?
Wave should travel twice as fast.
And what will happen when it will smash into the border of the screen?
If it's encoded well, it should just keep expanding out.
To where? Like going out of the display and going to the class?
Like the graph should just rescale unless there's like a wall set up on it.
Oh, I've been messing around. If the peak goes off to the right, it starts coming back from the
Yes,
left.
yes. So how do you call it? Everyone heard this? Let's try it and then discuss it. So I'm telling P naught equals, let's say, 7. File.
Particles in the box.
Or is safe? Oh, safe. Probably I should click on this floppy disk. Okay. And now I'm going to close all windows that are open by now and run it once again. So initial condition is the same because we didn't change variance, we didn't change width, and we didn't change the initial position. And later on, when we polish the code, we will write we'll label the axis. And now I click. What did you see? So it doesn't rescale the axis. It doesn't travel from the screen to the class. It reappears from where it disappeared. It is like if there I'm exiting the class, and instead of corridor, I immediately entering the next classroom. But this classroom will have a door, and a replica of myself will at the same time enter. Yes?
So at the very end, it started splitting. I'm not sure I should say splitting, but there was more peaks coming off that. Peak.
Yes, yes, because nothing is ideal.
Okay.
There are parameters that define precision. Each numerical computation, contrary to theory, has sources of errors, and errors accumulate with time.
Okay.
So if you decrease the step in position, increase the number of grid points in both position and space, then it will become more and more precise, no this additional peaks, and more computationally expensive. Right now, this all are jokes. It will run 30 seconds instead of half second.
Yeah.
But if you look for something realistic, then it can become prohibitively expensive. But if we follow the idea of London, who told like, why don't we redefine grid points as wave packet approaches the wall? But then if we increase spacing between grid points, our precision drops, and error will start accumulating more and more vividly. So it is a good idea if we need to explore infinite space. But if you don't, this is a healthy idea, because all our functions are mathematically well defined through this periodic boundary conditions. So where it doesn't drop on the border, but it just repeats from other side. And if we limit the value of momentum by the time of flight through the chamber, then we will never come into paradoxic problems. So limits of applicability of the theory is P naught is less than size of the box divided by duration of the overall simulation, and then we are safe. Make sense? Let me record it. So P naught should not be larger than cell size divided by simulation time. Note boundary conditions. Well, very soon we will reach the limit of human resources, and we'll start getting tired. But before this point, where should we go? What would be the natural way to go through? So we saw how to propagate, right? So inside the loop, you just implement wave function multiplied by evolution operator, right? So we know how to propagate. We found where the evolution operator is defined. And maybe you have marked it on your copies. So you know this. We saw where the Hamiltonian is defined. And right now we don't have the potential, it's just kinetic energy. We do not see where the momentum is defined. So probably it is what we should look before we faint because of being too tired. So where the P is defined. And maybe observables accumulation and output is too much for today. We will cover it next time. But for momentum, where the momentum is defined and how, what are the basic principles to define momentum, is something that we would benefit covering now. And also, it is related to the concept that we just reviewed, the concept of periodic boundary conditions. Like, where are they hidden? And the answer is, the periodic boundary conditions are hidden in the definition of momentum operator. So the variable, or it will be a matrix for momentum, will be px. So let's scroll for px and see. P operator. So this is version number 1 for momentum, but we will skip it because it is unnatural. Well, it's helpful, but not to start with. Let's go. So this POP is for P operator. Scroll further.
Should be above G tau 2.
Yes, should be about G tau 2. Yes. Let me see if there is another. They both are ugly. Well, all three are ugly, so I will better define them in the simplified way, and then we will look on how it is encoded in truth. I'm going to erase this plan because we already knew it, and next time I'll probably sketch it again. So it will be space for momentum. if our wave function psi2 is a vector, set of numbers, right? Then momentum, the operator should be which object? A matrix. And we can always check it. I'm talking too much. We can make more experiments like size psi2. Yes, I mean this 200. So it's just string of numbers. But if I do size of px, what should I get? This is something that you can answer confidently. Which, if the matrix, well, not the matrix, if the vector has 200 elements, and I want to design a matrix that will act on this vector without error.
200 by 200.
Let's check. Yes! See? So, momentum is a matrix. Now, what is inside? Who was presenting how to visualize a matrix? She's not at this session, but let me... So, open new figure. And what was her advice? Bar 3. Bar 3. And just in case, if it is not real, it could be imaginary. I will do absolute value of px. Px. Very ugly. Oh, better. So here is the px matrix. How do you like it? Let me introduce. Class, this is px matrix. Px matrix, this is class. So we do see that it is non-zero, very close to main diagonal. Then it is almost zero, and then there are non-zero terms just in very close to the edges, right? For this continuous change, we do not have time and wish. I will explain it approximately with less precision, but more clear human insight. So what is definition of momentum? So it is the only equation that, one of the very few equations that we need to memorize. Right? But we should understand that it is always applied to a wave function. And what is the definition of derivative? It means phi of x plus delta x minus phi over x divided by delta x. Right? So we need to define a matrix that will act on the phi 1, phi 2, phi 3, phi 4, blah, 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 and perform this operation. So it will merge together two neighbors, subtract them from each other, and flush them into phi 2 minus phi 1. Divide, well, you can put the rest out of brackets. Here it should be phi 3 minus phi 2, phi 4 minus phi 3. So we need to design such matrix that will convert this thread of numbers into this thread of numbers. Okay? Let me solve this inverse engineering problem. So, for the element number 1, we will have inheritance only from first and second elements of the matrix, right? And we use row by column, which means that first and second elements will be non-zero, and the rest will be 0, 0, 0, 0, 0. Okay? And then what will be the numbers here in order to implement this? So first element of vector will come with negative factor, -1. The second will come with +1. Okay? Make sense? Now, to generate the second element, we need to merge second and third elements of the original vector. So second and third. And the rest will be 0, 0, 0, and this one will be 0. Now, the number 2 should come with factor -1. Number 3 should come with factor +1. Right? Now, for the third element, we will combine third and fourth. This one and this one. And the rest will be zeros. Zeros, zeros, and zeros here. And they will come in the same pattern, -1, +1. So everywhere on the main diagonal we have -1, -1, -1. Above main diagonal we have +1, +1, +1. And the rest are zeros. If we apply some tricks of having smooth and more precise derivatives, we can put nothing on the diagonal and shift this definition in this way. Put minus here, 0, 0, 0, -1, -1, -1. So positive on one side, negative on another side. So it will be discrete representation of differentiation operator. Discrete representation of derivative operator. And then we multiply it by imaginary unit and h bar. Here I'm plotting absolute value. If you can check for real part and imaginary part. I make a bet that if I repeat the same command and request the real part, it should be 0. You can try it and check. If I request to plot imaginary part, it will be something like this, but half will be positive, half will be negative, according to definition of derivative. Yes?
And why did we change the diagonal?
Huh?
Why did we make the diagonal 0 and shift the negatives down? I missed.
Because we can shift, like, define that this will be not here, but first element will be 0, and then we can shift them a little bit within the continuity. I was not lying, but I was not expressing it in the elegant way. Wait, in 10 seconds I will answer in elegant way. We can skip point in between and use nearby grid points. If delta x goes to 0, the definition wouldn't suffer. Or we can think that we use the same grid points, but then we double number of grid points and skip those that we didn't count in between. Or, if you're still not satisfied, we can define the derivative as phi x plus delta x minus phi of x divided by delta x. But then we can add phi of x minus phi of x minus delta x, which is also correct definition. And then we take 1/2 of it. And then we carefully do it. You see phi of x is cancelled, and you see only one above and one below. I'm done convincing you in the elegant way. Hope it did work. So what do? Let's check. Let's try to catch me a line by doing replace absolute value to real and imaginary and see what happens. So bar 3 real. Well, it's not 0, but it is consistently small, I would say. Or maybe I made some big mistake. I would like to believe that it is just consistently small. Now, what if I do the imaginary? Rotation. Okay, so you see that to the left and to the right of the main diagonal is 0, and to the left and to the right there is highest and lowest peaks. So those would correspond to this +1 and -1. But there are ways to minimize the error, and instead of using only the nearest neighbors, one uses a formula that takes into account next nearest, but they are taken into account in the smaller, with a smaller weighting factor. And putting something on the edges would make sure about, we will implement boundary conditions. I think it is enough for today. So I will stay here and answer any questions, but please have some rest. Your day was maybe even harder than mine.
Oh, really?
It should solve it.